me some boards, please? Show me those boards and let's take a look. I see a lot of B first. I can't tell if I see it all the same, so I'm just going to take a look over here. So I'm frozen, aren't I? Huh, there we go. All right, B, A, D, C, whoa, what's going on? B, A. So look at yours, I didn't, but I could have.
No, never mind. No, never mind.
You guys all have the same answer?
That means it must be right.
Or it's not, and let's find out, because I don't know, because I don't actually know the answer. Let's find out. All right, so okay, the question said rank the magnitude of the velocity change of the blocks during a 2-second time interval. How did I do this? How did you do this? Brady, what'd you start with?
Pass.
Pass. Okay, I'll come back to you.
Well, C has the same force on both sides.
Okay.
I think that wouldn't be moving.
Okay, so
That's gonna be the smallest.
So we're gonna use some clever words here. We're gonna say maybe like the net force.
Yeah.
Does that sound okay?
Yeah.
Right? Because if you got 10 going this way and 10 going this way, the net force on it in the x direction is
0.
0. Hey, what's the net force in the y direction?
0.
0 also. We got the normal force pushing up and the earth pulling down. Yeah, okay, so we got net force of 0. So why does a net force of 0 mean there's no change in velocity? I'm going to open this to everybody. Anybody can answer that. Go, Tony.
Net force is 0, acceleration is 0.
Say that one more time. You said
Net force is 0, acceleration is 0.
okay, if the net force is 0, F net equals 0, then acceleration is 0. Sure. That makes sense because we know, we said this before, that F net divided by the mass was equal to what? Do you remember? F net divided by M is equal to the acceleration. Yeah. If you know anything from this unit, it should be this. That is it. Like this is it right here. This is Newton's first and second law. Okay? Yeah. If you wrote this down first and were a really good publicist, it could have been your law, right? It's not something that is mind blowing, but it is important. The acceleration is dependent on the net force and the mass, and so Bo says there's no net force. So Tony says, well, there's no net force. 0 divided by anything is going to be 0. So you got a 0 acceleration, or excuse me, a 0 acceleration. But this doesn't ask for acceleration. This asks for change in velocity. So take me to the last step. It's not a hard step, but it's an important one. Help me out. It doesn't say rank the magnitude of the acceleration of the blocks. What does it say?
Change in velocity. There's velocity change.
Yeah, and how is velocity change related to acceleration?
It is acceleration.
It is acceleration. Change in velocity, not just change in velocity, it's change in velocity over time. And it's important because the time is the same for all of them, right? So I don't want you to ignore the things that seem so simple because then there are problems where those simple things get changed and then it messes you up. So I want to make sure that you know that not only F net over M is A, but also change in velocity over time. The only reason that it can be the velocity change is because the time is the same for all of them. Because if this had different time intervals for each one, then it wouldn't necessarily be the same change in velocity. Does that make sense? So you've got to make sure you put all of those pieces together because otherwise it won't work. Okay. So you're telling me that the change in velocity for C is 0. I'm cool with that. All right. That's one done. And it was magnitude, so I can understand why you put that as the least, because 0 would be the smallest magnitude you can do. All right, help me out with the more. Yeah, with the others. I speak well. Go, Chris, can we start next?
The F net magnitude for all of these is 2.
Oh, it's 2 for all of them? Because I've got 8 minus 6 and I've got 8 minus 6 and I've got, oh, it's 8 minus 6 for all of them, right? So F net for all of these guys is 2. F net, now it's not in the same direction for all of them, is it? Because the A and B are the same direction. D is the other direction, but because it says magnitude, that means we're okay, right? Okay.
If you divide F net by mass for all of them, you'll get 2 over 4 for A and B, and you'll get 1 for B.
2 over 2, 2 over 4. Yeah.
And 1 is bigger than 2 over 4, which is equal to 2 over 4.
Hey! That's awesome. Yeah, so 1 is bigger than 2 over 4, so that's where B comes from. And then you've got A and D in alphabetical order, right? Not wrong if you read it the other way, but there you go. Okay? So, I want to make sure that even if you get it right, even if you and your table mates write down the correct answer, that doesn't mean your brain turns off, because it's the reasoning that matters, right? On an AP test, they do these. They love to have ranking tasks. And when they do, if you don't write good reasoning, you may or may not get a point for the answer in and of itself. So it's the reason that matters, which is why I always take time to talk about that reason, because that's the piece that matters. We doing okay? Speaking of reasoning, go ahead and get that gold sheet out that you did for today, the one from your homework. So I was looking at this. I was like, oh man, they're going to love this. It's just like a 2-column proof, right? Did you notice that? It was kind of like a 2-column proof of this. Yeah, you can do it. So, yeah, I can totally get yours cut. Did you guys see that too? Wow! Oh man! Okay, I need to do this right now because I want to make sure that we're using our time wisely. Please cover up your eyes with your right hand and raise your left hand in the air. Oh no! Cover up your eyes with your right hand, put your left hand in the air. Okay? True confessions, no judgment. Raise your hand, or leave your hand in the air if you completed this thing. Okay. Everybody put your hands down. Everybody open your eyes. Okay. This is what we're going to do. I don't want to waste time doing something that you haven't all done. So, put that away. Do it for tomorrow if you haven't done it yet. Okay? Don't make this a habit or I'll start collecting them the day of, which makes me really crabby and makes you crabby also, right? Okay? So put it away, do it for tomorrow. I don't want to waste my time teaching you something that you can learn yourself. All right, we are going to go ahead and introduce something else differently, okay? So we're going to talk about another force, one of the forces that is coming into our realm of knowledge, okay? And that is the force of friction. Tell me really quickly, well, I'm going to do it this way. I'm going to give you 1 minute to write down as much stuff as you know about friction. Go. You can talk to each other if you need to. Write stuff down. 1 minute. I'm going to time it. Go, go, go. So fast.
Are we going to do a lot of things?
I don't know, like half a page? All right, we're going to resume. We're going to come back and we're going to talk. We're going to go around table by table. Tell me what you know. Tell me something you know about friction. Go. You said a lot of things and they were all right, so go ahead and say one of them out loud. Go, go. Oh, you're supposed to write them down.
It refers to things are rubbing against each other in opposite directions.
2 surfaces.
Disperse them.
Oh, 2 surfaces. I'm going to say moving relative to one another. Is that okay?
Sure.
Yeah, but it's the same thing. Two surfaces moving relative to one another. Then I saw you guys doing this, right? This is some 3rd grade science. Your teacher said, okay, go, 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 go. All right. Oh my God, you did it with friction. Yeah, you did this. I know you did. All right. Table right here. What's another thing you said?
It releases thermal energy.
Ooh. All right. Go here.
It starts with an F.
It does, and so when we write down the force of friction, we are going to write it as F sub F.
Yeah. Yeah.
Okay.
You said it's like how two like things would interact with each other.
Mhm.
The ability to like slide between each other.
Okay. Yeah. So it can slide or stick. Right? If you have very low friction, then things are going to slide. If you have very high friction, then things are not going to slide. They're going to stick. Yeah. All right.
Like air resistance is friction caused by air molecules.
Mm-hmm.
I mean, it could be friction, just like being on the surface. If you had a surface that was, in theory,
So what did you say? Hold on, because I'll come back to this. So you said air resistance is, what did you say?
Friction caused by air molecules.
Awesome. Thank you. Whoop. Awesome. Can you want to add something to that or say something separate? I'm not sure.
How to word this in a way that's, I guess I know, I just can't think of how to word it. If you have two surfaces, they're not really, even if it appears to be a smooth surface, it's really not. There's little balancing little things that make it rub into each other, and that's what creates friction.
Yeah, so keep talking, sorry.
In theory, frictionless surface would be something completely smooth, which would be kind of cool, because then you could slide, you just never stop moving.
Right.
Except if you were in a vacuum on a frictionless surface, you'd never stop moving.
That'd be awesome, right? I'm gonna take what you said there one step further. So all surfaces have friction due to little bumps. So even like these tables, which feel like they have very, very little friction, right? They're very smooth. But if you looked at them from a microscopic level, they are really bumpy. They've actually got lots of pits in them. Yeah, yeah. And so you said that if there was no friction, then an object would what? It would not stop. It would just keep going. So let's flip that over the other way. So because of friction, what happens?
It causes the object to stop. It creates resistance.
Okay, so friction causes to stop. And does it just make them stop automatically, like immediately? Or are there some more physics words that we could add into that?
It creates a negative acceleration.
Woo-hoo! Yes! That was awesome. Yes. It creates a negative acceleration. Another way that we could say that I like that was like that's gold star material there. I'm also going to say that it opposes motion. And I'm hoping that I didn't just steal yours. So did you guys have anything else back there? There are lots of good things.
No, that's basically everything.
Yeah? I didn't mean to give you the hour. I really wanted to know what else you guys said. Did you have anything else? Maybe not.
You have something.
What's that?
It's gonna slow it down.
It's going to slow it down. Yeah. So it's going to cause it to stop eventually. It's going to have a negative acceleration. It always opposes the motion. Okay? So these are all fantastic things. I really appreciate that. So one thing I'm going to highlight here is that it's two surfaces or a surface interacting with air molecules. So it's really the surface of the molecule. So it's still kind of the same thing in any of those cases. We've got surfaces that are moving and a frictional force. So we're saying it's a force of a surface on an object. Didn't we talk about the force of a surface on an object yesterday? Was it friction? Because I don't think we talked about friction yesterday. What surface force did we talk about yesterday? Look at your pink sheet if you haven't already. That's going to be the place where it'll tell you. The normal force. The normal force was also a surface on an object. But what do we know very specifically about the normal force? Is the normal force a frictional force? No. The normal force is, what'd you say? It's perpendicular. I want you to think about a frictional force. Do you think a frictional force is ever going to be perpendicular to a surface? No. In fact, it's the opposite of perpendicular. What is it? It's always going to act parallel to the surface. So there are kind of three big things here. We need to know that it's the surface on the object. We need to know that it always acts parallel to the surface, and that it always opposes motion. Okay, those are like the big three. Everything else you guys said here is absolutely great and fantastic, and I'm excited about it. But these are like the big three. If you're going to take anything away from today, those are the three. Okay? One other little piece of information is that there are actually two different kinds of friction. Does anybody know what those two kinds of friction are? Oh, yeah. Yeah. Number one is static, and the second one is kinetic. Have you ever heard those words before? They were in the problem. Ha-ha, resourceful child. Have you ever heard the word kinetic before? If you have, what have you heard? Like, in what context? What's that? Kinetic sand. What does kinetic sand do? It sticks together, but also kind of moves, right? Like the idea is that it's like it moves in your hands and it's really, Kinetic means moving or motion, okay? So kinetic friction is the friction associated with motion, okay? And if we can use our reasoning skills, if I've got kinetic friction, which is the friction involved in moving, then what do you think static friction might be, friends? Oh, look at you guys! You're so smart! That's great! Yeah! Not moving or no motion, we'll maybe say. Okay? So if we're going to measure these things, we can measure them, and you're going to do this in just a minute, but I want to show you this because it's kind of cool. We can measure forces using this thing called a dual range force sensor. A force sensor, basically I can pull on it, and it will measure how much I'm pulling, or, because a force is a pull or a push, or I can push on it. I'm going to show you how this works here. Hold on just a second. I'm going to switch this over so you can see it. And then we will get started with the lab. Go thing. Okay, so when you graph this, just to kind of remember this for tomorrow and, future times. If we graph, this was force on the, because I know you guys like graphs too. I remember that conversation we had at the beginning of the period, so I want to make sure that you can appreciate this. So this is the force. This is really the applied force, but does it make sense that the applied force is going to be related to that frictional force pulling back, okay, over time? And I'm going to draw it a little bit maybe more cleanly than it looked on the computer. But it's going to go up, 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 up. And then it hits some peak. And then what happened after that? Then it goes down. And then it stays that constant. Okay? So it goes down and it goes. Okay? This part right here, this is the static friction, and this part here, this is the kinetic friction. So I didn't print off a lab for every person because I felt like that was kind of a waste of paper. So there'll be one for each lab group to work with, but I'm going to go ahead and just show you what the lab looks like. So you are going to be asked to investigate a couple of questions. In fact, I'm only going to have you do one, just given the time and given kind of where we're at. We're only going to answer that first question on there, so you can ignore, when you see this, you can ignore that second question. This is a picture of exactly what you just saw a second ago, okay? We're going to design a procedure to collect data that allows you to answer that question. Each person is going to submit a completed Google Sheets analysis with raw data and process data, okay? And appropriate graphs to show me how you're answering the question. And then just like a 2 or 3 sentence conclusion. It doesn't have to be a long paragraph, okay? That's the information that you need from me. There's some technical things here that you'll need to know as well, but I'm not going to read these to you because number 1, you can read, and number 2, it's not going to mean anything to you until you start getting set up, okay? Each pair or each group is going to need a Chromebook. You will also need to get a block and a set of weights, and then there are also what am I trying to say? Sandpaper over there. If you want to use sandpaper instead of the table, you are welcome to do that. Please make sure not to put the sandpaper sand side down on these tables because it will ruin the table. Okay. The computer equipment that you will need is over here. Okay, you'll need one of each of those boxes. Okay, and I'm just going to get started. I'll come around and help you as you need. Sound okay?
No, I'm not.
Great.
Or sideways. Oh.
You guys get on the
Nice.
What's your drinking?